Hello, everyone, and welcome to the 42nd Surface Ventures keynote webinar. Good to see some of you already typing in the chat, but for those of you that haven't done that yet, please say hi in the chat. Tell us where you're joining from. It's always great to see the huge range of places that people register and watch our events from. My name is Dr. Sam McMaster. I'm the content manager here at Surface Ventures, and we are a non-for-profit organization, and our mission is to provide world-class surface and material science education for both academia and industry. So today it is my great pleasure to introduce Professor Carsten Garchow of TU Wien. Carsten received his PhD from Saarland University in Germany in 2012, where he studied the effects of laser interference patterning on the microstructure and topography of metallic surfaces with a focus on tribological applications under Professor Dr. Frank Mücklich, and Professor Dr. Martin Musa. For his work, Dr. Garchow was awarded the European Honda Initiation Grant in 2011. Professor Garchow was academic visitor with the Tribology group at Imperial College London and is currently head of the Tribology Research Group at TU Wien. Additionally, Professor Garchow is visiting professor at Pontifical Catholic University in Santiago de Chile and chief editor of the peer-reviewed journal Industrial Lubrication and Tribology, the Emerald Publishing Group in Leeds, UK. Please welcome Professor Garchow to the stage now. And many thanks also to today's partner, Artec Instruments. We'll have a short presentation from Philip Kemp later in the event, who please also come to the stage to say hello. We'll be releasing poll questions and handouts from Artec Instruments later in the event. As we go along, please type your questions into the chat and they'll be marked for the Q&A sessions. We're planning to go for around 60 minutes today, and we'll be sharing a link for your attendance certificates later in the event. Welcome both, and thank you for being here.
Thank you.
Pleasure, yeah.
Okay, so with that, let's proceed with the talk. So let me bring up your slides, Professor. There we go.
Yeah, fantastic. So great. A good afternoon from Vienna to all of you, or in some places it's already a good evening or very good morning. But in the next 45 minutes, I would say we are having the pleasure of staying together, and I'm actually ready to tell you some lessons learned from 2D materials and tribology. So first of all, I would like to thank Surface Ventures for giving me the chance today to present the work we are doing in our group. So I chosen the title Lessons Learned from 2D Materials and Tribology. Actually, what I'm going to show you in the next, as I said, 45 minutes is some of the stuff we did in the recent past about our research at TU Wien, in our research unit of tribology at TU Wien. And the first thing I would like to start with is actually the relevance of solid lubricants in space. You know that we have several problems now on Earth. We have actually overpopulation, we have energy crisis, we have a lot of problems with resource efficiency. And tribology is one of the things we can actually use as a very useful tool if it comes to energy that is consumed worldwide. We know from numbers from Ali Erdemir and also Kenneth Thornburg, and that has been reported many times. And most of you from universities and academia, you know about these papers telling that around about 23% of the world energy consumption is consumed by friction and by wear. So 20% roughly of friction and 3% actually spent on wear of components. So because of that, and because of the demands we have right now in our society, people start looking far away, looking into space to see if there is something out there where we could maybe in the far future we could have a second Earth, or where we can have a place where we can look for resources, for minerals, for things that we are running out in the next couple of decades, maybe. And for doing so, of course, we first have to look into space, what is up there. And we need devices that work, of course, far away from the Earth. One of the spectacular things that I came across also some longer time ago, the same as maybe you, is the James Webb Space Telescope that caught my attention. It's a really fascinating device. Just wrapped up some of the basic facts of this device. You can see it's a $10 billion project, so it's pretty expensive. The sunshades of this telescope are as large as tennis courts, so it's pretty big. It's located very far away, so 1.5 million kilometers away from the Earth, which makes it difficult to get it repaired. And it also has around about 7.5 tons weight, which equals one adult African elephant. Actually, this tells a lot about the elephant as well. I didn't know before that an elephant, an adult one, can be that heavyweight guy, but obviously, yes. So one of the issues we have, if it turns about lubrication in space, tribology in space, is the fact that everything needs to work reliably. If there is any issue, with friction, wear, lubrication in general, then one of the big things is you cannot simply go up there and say, I will repair it in a second. It's simply too far away, and there is no possibility to get the things arranged again. So once you boost that up with NASA or ESA or whoever is launching that, now we also have two other gentlemen like Jeff Bezos and Elon Musk, of course, who also are sending rockets up into space from time to time. With all the pros and cons, of course, but the thing is simply that we have to rely on what we set up and what we launch either in the orbit or even more far away. Interestingly, when I think it was 1.5 years ago, I was following on LinkedIn some news about the James Webb Space Telescope, and I found this short report here with the title. I just copied it out. James Webb Space Telescope has a friction drawback that NASA wants to repair. Well, first question is, how does NASA want to repair that? As I said, it's not that easy. And the other thing is what finally got broken. And what was actually broken is maybe from some reports about the space telescope, it is an infrared telescope, and it has different ways how it can change between the different modes for infrared inspection. And one of these gear wheels actually got problems with the molybdenum disulfide coating because of humidity. And that is when the things got stuck, and we had really severe problems. Finally, they solved it. I don't know exactly how NASA solved it finally, but the major issue was actually humidity. And as you may know already, that molybdenum disulfide is a very good, a very high-performing solid lubricant, but only if there is no humidity involved. Now you can say, but it got up into space, so where is the humidity issue coming from? So actually, when you assemble the stuff here on Earth and then you pack it, you send it up, of course, somewhere in this chain of processes, it may have occurred that the MOS2 got some humidity issue. And so, it finally failed in its performance. And what happens if lubrication is not really good? You can see in the lower right-hand part of the slide, you see this is a bearing that was actually strongly influenced by obviously by friction and wear because of a loss of lubrication issue. And even if it is made of very hard, very tough steel, you can easily see that the things are getting destroyed immediately. So for the future, even if we take some more missions on Mars and with Mars rovers and Mars devices, it's pretty clear that we need something that is really 100% reliable. The next stuff is, and this is part of the truth, and today I do not want to tell you only the hero stories of what tribologists are doing in the field of 2D materials. No, I also want to be very honest with you, telling you the stories where things are not working. I think that is in science very important, that people get into getting knowledge about things that do not work. Because if everybody is telling you what is working fantastically, actually there is no real learning, and also it's sometimes a waste of time to repeat stuff where other people already showed that it doesn't work. So one of the truth points is that, of course, the lubrication in space is not only based on solid lubrication. We also have a lot of liquid lubrication in space. You see some examples here. I hope that you can somehow read that on the slide. So there is Mars rover Curiosity. You see this is a liquid lubricant that is based on multiply alkylated cyclopentanes, so-called MAC oils. But we also have on the ISS various products that are from various companies provided. One of the big issues is that in order to get them operated in space, they need to be either heated up to a certain operating temperature. And this requires, of course, additional infrastructure, additional equipment to heat up. And when you have additional infrastructure, of course, it's additional weight. And that's problematic if you want to have a mission up to space. So things in the future will maybe transform more and more in the direction of solid lubrication. But maybe to summarize a little bit again, what are the problems associated with liquid lubricants? So first of all, of course, as I said, we have a limited temperature range or atmospheric pressure range in space, and not all the lubricants are recommended to operate in these conditions, under these conditions. And then, of course, we need a confinement, and this confinement should, of course, keep the oil or the grease in the right location. But we also have, like in the deep drawing, metal forming applications, we have the issues with environmental concerns. So a lot of waste disposal that is created either by this metal forming processes. You have to oil the surfaces. Then when you are done with the process, you have to degrease or de-oil the surfaces again. And that is another time-consuming step. But also you have, of course, a lot of waste that is produced. And that's why I say the attention turns to solid lubrication. And you can use a big zoo of different materials that come into mind. So soft metals like, of course, tin, lead in the past, but lead nowadays is something people do not want. That's pretty clear. It's toxic. We have polymers like PTFE, Teflon, where we have now in the European Union, of course, a discussion about PFAS ban. And we do not know right now where to go with this PFAS ban. So up to now, they say it might not affect the entire product palette, but in the future, who knows how it will end up with the Teflon. And it is very clever and smart to really rethink already some of the materials and maybe to have an opportunity, another option or a plan B in the pocket in case of it is really getting banned. Then there are another couple of things like hard carbon-based materials, DLC, fluorides, which can be used at higher temperatures, but also binary and ternary oxides, and finally 2D materials I'm going to talk about today. The first slide is some of the stuff we did some longer time ago, but it was a very nice cooperation. So we have a couple of people who worked with me either in my team directly here at TU Wien. There's like Philipp Kutzmacher, who is now working at Scheffler Company, who was working in my team for many, many years and did a great job. And then there are some other gentlemen you may know from seeing the picture. There is Ali Ademir here on the lower right-hand side, but also Giovanni Ramirez, a good friend of mine who is working now at Zeiss, and Paul Meyerhofer and Helmut Riedel, also both professors from TU Wien working in the field of coatings of materials. And the first thing we did is we investigated again the performance of transition metal dichalcogenides, such as MOS2 or WS2. Today, I'm going to talk about selenides a little bit, because we know that actually selenides and tellurides are, let's say, more efficient if it comes to friction and wear compared to MOS2 or WS2. Although I would still say that MOS2 is, of course, the gold standard if it comes to solid lubrication under vacuum conditions. And one of the problems is with the solid lubrication, once it is actually get worn off or it is consumed in the tribological contact, the replenishment of the contact with the solid lubricant is a big issue. So with oils and greases, it's pretty straightforward because you can simply put it to an external oil pump and you can replenish the contact with oil. Or if you think of a bearing, you can simply grease the bearing, you can seal it front and back side, and then you have over the entire lifetime of the component, you can secure and you can be sure and guarantee that lubrication is actually working. But how do you do, as I said, if it is wiped off or if it is just worn off, rubbed off in the process? The human body, as another example, is very smart in doing so. I mean, the lubricant that we are using in our cartilage is formed depending on the demand in our joints. And also, if you think about still the good old internal combustion engine, where you have motor oil with certain additives, and these additives, I always tell my students, it's like the spices in the soup. You can cook the soup just with water and salt and that's it, but it's not very tasty. But if you put some additional spices and herbs inside, the things are getting very tasty. And the same is with the oil. So once you have an oil with certain additives inside, they may influence different things like corrosion behavior or viscosity index, friction modifiers, anti-wear agents. There are many things you can do. And one of the most prominent things maybe is ZDDP, which is a zinc, sulfur, and phosphor organic compound that actually tends to protect surfaces with a tribochemical layer, which is typically in the range of 100 nanometers, 150 nanometers, but it's very powerful and very protective. This is all true for oils, for greases, for lubricant in the human body. But again, coming back to the solid lubricants, how do we end up with this? I mean, one idea could be that we are using, for example, nanoparticles of elements we want to have a kind of an in situ reaction together with catalytic, in this case, molybdenum or tungsten coatings. And that is exactly what we did. And the picture is as simple as you can see it here on this slide. It's like a pepper or salt strayer. You just put the powder inside of the contact, and then you, under the action of shear forces and temperature, you actually create on these catalytic surfaces either molybdenum diselenide or tungsten diselenide, but in operando or in situ in the moment you apply it, and you start the rubbing process. So we did this, and interestingly, you can see here some of the results we obtained. On the left-hand side, there is the molybdenum substrate. The black curve is simply molybdenum. There is no particles on top. There is no oil, no grease, nothing. You see, we end up with a coefficient of friction in the range of 0.6. But once you add the selenium powder, selenium nano powder to the system, you see with the red curve how the friction is decreasing here significantly. And we end up with a value around about 0.09, which is also reproducible. So even after some time, if that goes up again, you just put again some powder from your salt spray to keep the image, then you will end up again with a very low friction for a long time. And the same is true for the tungsten substrate, where we also observe a drop in the coefficient of friction from 0.4 to 0.13. And if you look at the wear tracks, the respective wear tracks, you can see that it also works. So it's not even reduction in friction, but you also see clearly that the wear track doesn't look so severe in case you add the selenium powder or for the molybdenum surface, but also not for the tungsten surface. So this seems to work, and it is also reproducible. The next step was that people asked us also in the review process when we published, or we tried to publish the paper first in Advanced Materials. It came back and the people said, you know what, it's just because you have a powder and the particles are rolling, and then that's the reason why you have lower friction. And then Philip actually had an idea and said, you know what, we are going to do another test. And in this test, actually, we proved that it is not because of the powder, not because of particles. It's really because of the in situ tribochemical reaction that takes place. So just to guide you through the diagram, you see this is, so to say, the measured curves with the average values, and everything, the fluctuations you see, the oscillations you see is the standard deviation in the measured coefficient of friction. So the blue curve is actually the steel reference. And then you see there is a purple curve, or let's stay for a moment with the black curve, that is molybdenum, pure molybdenum, and this is the pure steel, no particles. If you are adding to the steel surface selenium powder, you see it in the purple line that the friction goes down, but not really dramatically. It goes a little bit down, but if you are using the molybdenum surface and you are adding the selenium powder, you can really see a remarkable drop in the coefficient of friction. So This is the reason why we say it's not because of the selenium powder itself, it's really because we have a tribochemical reaction in the system. And then you can go further. You can, of course, make TEM, and you can also confirm by Raman spectroscopy that you actually do form the selenides in the contact. And when you do this, you see the upper line here is for the molybdenum surface, and the lower line from D to F is for the tungsten surface. You can measure the lattice spacings, and that is actually exactly what we find in literature, which is documented in the literature. So the lattice spacings really match very nicely with molybdenum diselenide and tungsten diselenide. And the same is true for the Raman spectroscopy, by the way, where you can also detect the selenides, the respective selenides in the contact. So this seems to work. It's a very nice approach. The next chapter I would like to talk about today is actually MXenes. Also some of the friends and colleagues you see here, also Andreas Rosenkranz from Chile, who is a good friend of mine, and also Yuri Gogotsi, who is, let's say, the pioneer, the godfather of MXenes worldwide, and also people from AC2T research in Wiener Neustadt, like Guido Boidi, but also Babak Anasori from Purdue University, are people with whom we collaborate from time to time in the field of MXenes. MXenes is very interesting. I mean, you can see here a little example of how these materials look like in an electron microscopic image. It's like a stack of papers that are shuffled together. And of course, the number of publications rised over the years dramatically. You can see here, especially in Asia, there's a huge boost up in publications in the field. Actually, MXenes are not super new. They have been discovered in 2011, and they have been mainly investigated in the field of energy storage, desalination, optics, catalysis, and these kind of fields. And then people came across and said, hey, there is no information about tribology. Would you think it made sense to test it? We started. Andreas also did great work in that field and still is doing a lot of research work in that field. And we saw that actually MXenes have very interesting properties. And maybe just a few sentences where we are getting MXenes basically from. So they are based on MUX phases. So this is something like titanium, carbon, and aluminum, which is synthesized at a certain temperature, certain time. And once you get this MUX phase, what you are doing is you etch out the aluminum, and the remaining material without the aluminum on board is actually your MXene. So because of this similarity to the MUX phase and because of the layered 2D character, like in graphene, that's the reason why it's called MXene as an artificial word. So the tricky part is etching actually the aluminum out. So we are usually faced with HF, which is a very nasty chemical substance. And everybody who worked in the field of chemistry labs, they know that HF is really not a good friend. And one of the major things is if you end up with the MXenes, you have to functionalize them. And there are different functional groups available. This can be oxygen, can be fluorine, chlorine, can be OH termination. So different terminations, different materials are available. As you can also see here from the periodic table of elements, it's not only titanium, it can be vanadium, can be niobium, molybdenum, and many, many other things. But also for the X here in the formula, it must not be carbon, it can also be nitrogen or even carbonitride. And for the surface terminations, I already told you that there are as well many, many things you can use for the surface termination. So overall, it's a very demanding process, and sometimes companies are calling me and say, hey, we would need for an application 1 or 2 kilograms of MXenes, and then I have to disappoint them and say, we don't have 1 or 2 kilograms of MXenes. We can get maybe some small amounts in the range of grams if we are lucky. So there's still an issue with the upscaling of MXenes, although there is a lot of progress ongoing in the research community, and people are now able to produce larger amounts, but still, I would say, if you compare it to other materials of choice for solid lubrication, there's a huge gap in the upscaling. And one of the things that are really getting nasty by time is with this etching with HF. There are many different routes you can take to avoid HF. and it's also something we are working on. But before that, I would like to simply show you some of the examples of the tribological performance of MXenes. This is some work we did with Philip and also Andreas from Chile and other collaborators worldwide, where we studied very simple steel reference surface with a MXene coating on top by electrospraying. You see here again the data on the left-hand side. Contact pressure in the range of 307 megapascal was the silicon nitride ball, certain speed, certain stroke. And the first tests look very, I would say, promising. Yeah? You see that you can really reduce the friction. And also, if you do the tests at a longer cycle number, you can clearly see that even at a higher cycle number, the things are still running. Although at maybe in the range of 60, 70, 80,000 cycles, there are more and more friction instabilities popping up. But it's simply because of you have wear debris, particles in the contact, and then of course you have these jumps in the friction signal, which are these instabilities, but I would still say nothing severe, nothing critical. The next thing is what you can do, and this is not from our group, but this is from collaborators. In that case, Papaganasori's group. You see that even if you do it right, with the right counterbody, and you even involve DLC coatings in the game, you can even get super lubric. Super lubric would mean that you have a coefficient of friction lower than 0.01. So, you know, in tribology, everybody dreams on this scenario that you have vanishing friction, that things are running very smoothly. This is what we call super lubricity. And there are different ways to achieve super lubricity. So if you do it right, even with the MXenes, you can go to super lubricity. On the right-hand side, this is a more application-oriented example. This is by Max Marian. Also together with Andreas Rosenkrantz and Stefan Dremmel and other collaborators. They could, interestingly, they could show that if you take a bearing and you deposit MXenes on the raceways of this bearing, and you look at the overalling numbers until the end of the service life of this bearing, you see in green here, these are the MXene-coated species. The blue one is MOS2, so the gold standard in solid lubrication. And the other ones are even involving DLC coatings. So the number of overrollings until the end of the service life is best for the MXenes. And this is really in the field of bearing applications. So it's not only a fantasy from the science and research friends, it's also something that really can be applied in industrial applications that seems to have really big potential. Another example recently that we worked on with colleagues from AC2T in Wiener Neustadt. Again, there was also Andreas Rosenkrantz on board and Philipp Krützmacher, Markus Wager, Manel Ripoll, Guido Boidi, and others. We tried to see the effect of hybrid coatings in a way that we have MXenes and MOS2 together. Why? Because we know MOS2 has also some drawbacks. I told you about the humidity issue. And MXenes also, they have some shortcomings, especially about oxidation stability. So they tend to oxidize depending on the surrounding conditions very fast. But also, I mean, we know that a certain contact pressure is required to activate them. But if you exceed a certain contact pressure, let's say 1 gigapascal, they even may degrade pretty fast. So we try to combine these two materials and try to bridge the gap between the disadvantages they have. And you see very nice diagram here. So the reference here in a blackish looking line, which is simply a ball bearing steel surface, 52-100, 100 chromium 6 discs, and also ball material. You see in blue the MXenes. You see in red the MOS2, and you see for green and yellow a composite coating or hybrid coating, MXenes and MOS2. The composite one is actually just a mix of MXenes, 50% with 50% of MOS2, just randomly mixed. And the composite number 2 is actually consisting of a MXene layer at the bottom and MOS2 layer on top. And with the same thickness, more or less. And you see very nicely that if you combine these two coatings, that the friction signal is very stable and even beyond this test, what we found out. And if you look at the MOS2, for example, at a certain point, it starts to get up, but also the MXenes, they already start to increase long time before the composite coating. So obviously, this is something where we can take the advantages out of both systems if you simply combine MXenes and MOS2 coatings. Yeah, this has been tested with an SRV5 from Optimal company, where we have also varied the contact pressure and also the temperature. So here I just show you the room temperature measurements, but if you look into the publication that is cited here, you will also find more results referring to higher temperatures. Another idea was to say, okay, because we worked in the past a lot in helicopter gearboxes and alternative lubrication scenarios for helicopter gearboxes, was to use MXenes together with ionic liquids. Ionic liquids are interesting because they have, let's say, a very low flammability point. They have also, they are not so volatile, so they are very stable. They have very good thermophysical and thermochemical properties. And we came alongside with the idea to mix or to blend MXenes with ionic liquids. For this purpose, at our university, we selected 2 different ionic liquids. The cation was for both ionic liquids the same, and only the anionic part of the ionic liquid was actually modified. So for the number 1, it is a methyl group, and for the number 2, it's a butyl group. And what we did is very simple. We have a rotating ring here pressed against the cylinder. It's called in German version Brucker test, according to this DIN here, the standard. And we just applied a very low amount of liquid. It's around about 8 milliliters. And we measured the load carrying capacity of the blended mixture compared to, let's say, standard turbine oils, how they are getting used in the helicopter industry. And interestingly, if you look at the combinations of the ionic liquids with the MXenes, they even outperform in terms of the load carrying capacity the standard turbine oils that you can buy on the commercial market. So that was really surprising to us. But one has to be honest and to say, of course, that these turbine oils have different additive packages, and that, of course, the additives inside are not only made for a high load carrying capacity, but still, I would say it's a very nice result if you look at the performance of the ionic liquids together with the MXenes, how much of the performance you can get out of it, out of this just by using a very simple mixture of liquid lubricant. And something new that comes into our mind, we're currently working on, is the combination of what I did many years ago in my former scientific life, that is laser surface texturing, where we actually have a project together with Polish partners, and it is about biocompatible surfaces for implants, where we combine laser textured surfaces and MXene coatings. And interestingly, if you combine, you see some examples here for different surface textures, so line-like textures, but also cross-like textures. And if you measure the coefficient of friction, you see that this combination for steel, that is the upper right-hand side diagram, but also for titanium, that's the diagram underneath it, you see a very clear and significant improvement in the friction behavior if you combine coating and laser surface texturing. So obviously, the surface textures are acting like a reservoir where you put the solid lubricant into the pockets, and they are getting into the contact from time to time if needed. And on the other hand, of course, the coating is simply protecting the surface of the laser surface textures by not getting abraded too fast. So it's a perfect synergetic approach where you can really benefit from both worlds, and something that you can easily adapt by simply using air spraying or electro spraying. The only thing you need to be careful of is, of course, to make the right dispersion. So to keep the MXenes, of course, in the right dispersion, and then to apply with, as I said, air spraying or electro spraying is the way to go. Just another picture that shows how nicely that can be done. You see here the MXene flakes on top of the surface texture in a FIB cross section, and actually the MXene flakes very nicely replicate the laser textures, and they can even be found in the recessions. As you can see from the TEM investigation here, you have a lot of MXenes in these pockets, and if you look closely, You even can see the lamella 2D character of these coatings in detail. And if you measure that, you will also come alongside with the typical lattice spacing of the MXenes reported in literature. So this works, and this is a very promising approach. So as pointed out in one of our previous publications, maybe MXenes do not give you at first hand a very low friction coefficient. You can even go super lubric, but it needs a little bit more, more challenging adaptations to your system. But what I think is the makes the big difference between other candidates is definitely the normalized wear life. And if you look in this diagram, so the red star here in our diagram definitely outperforms all the other candidates that are well established already on the market. So it's very promising. But we also have to be honest at some point that the sustainability of MXenes still have some question marks. First of all, if you look at the titanium-based ones, you should take care of how to recycle your titanium. You also need a couple of other elements for the synthesis of the MXenes, depending on the kind of MXenes you're investigating. And this is simply to highlight, of course, that we need to have reliable resources to be able to produce MXenes. If you look more deeply into the process of MXene synthesis, you will also learn that on the left-hand side here, you have a lot of very energetic processes. You need to have the production of titanium, there is graphite production, there's aluminum production, you have a lot of electricity involved, there's wastewater and gas emissions and so on. And all this stuff, of course, needs to be taken into consideration. So to make the story short, I mean, you can have super cool ideas in the future for solid lubrication, but of course, you always have to now take care of the questions about resource efficiency, sustainability, and also toxicity, because you can have certain tellurides. They have remarkable friction reduction and wear reduction. But if you apply it and people are getting sick or even worse, then it's not the way to go. So you need to have a kind of a compromise between frictional performance, wear performance, but also availability, upscalability, toxicity, and sustainability. If you don't consider all these factors, you will definitely run into several problems. And just to complete this topic, this is again from Babak Anasori's work that has been published in Advanced Materials. And you can see that there is the production of industrial aluminum compared to industrial copper, compared to 1 kilogram of titanium-based MXenes. And the green bar is simply the reference. It is simply normalized on the MXene synthesis. And you see, it doesn't matter what kind of energy you take, nuclear, geothermal, fossil, biomass, wind, water, solar, primary forest. For all of these, actually, the production of MXenes is very energy intense, very intense. So there's only for water, actually, there's interestingly for water, you see a kind of a very close race between the industrial copper production and the production of MXenes. But for all the other energy sources, it's very energy demanding, the process of MXene synthesis. But after some time and upscaling the processes, we are very optimistic that we can really get the things done in the right direction. Yeah, this is what we are currently working on, and this is also something that we just resubmitted to Advanced Materials after the first revision round. We are actually working on a green approach to synthesize MXenes by electrochemistry. This is work done by Markus Ostermann and also Pierluigi Bilotto from my group, together with Markus Fatina and also colleagues from AC2T, where we try to avoid completely toxic chemicals, where we also try to be fully green in the synthesis, and where we are using pulsed electrochemistry as a way to go for the MXene production. And in case this works out, and we are very optimistic, this can be really a game changer in the future to have a green way to synthesize MXenes. Yeah, last short chapter. If you have heard a lot about, from my side, TMDs again, also MXenes. And I said in the beginning that both systems have some shortcomings. It's either the number of active sites or the oxidation stability or the humidity influence, temperature influence, and so on. So one new group of materials we are right now working on are transition metal carbochalcogenides, which is simply called TMCCs. And the TMCCs is a kind of a very smart combination of TMDs and MXenes. So actually what you have is a core of MXenes with a surface that is made and designed of TMDs. These materials are interestingly not completely new. They are already known for some decades, but they have been never applied to tribology. And also nowadays, with our collaborators in the US, Professor Michael Najib's group, they are able also to produce delaminated ones, which are interesting for tribological applications. There are two candidates we have been working on. Just recently, there is a niobium-based system. You can see here it's niobium 2 sulfur 2 carbon. And the same also is true for a tantalum-based system where you have tantalum 2, sulfur 2, and carbon. And these two systems are very interesting. So you start with a chemical approach here. You see it sketched. If you want to have some more information, then you can simply look in this advanced materials publications from our collaborators. And you typically end up with something that has intercalated atoms, either of copper or of iron. And depending on the intercalation, it's very interesting to see the effect on the friction behavior. So again, we made measurements here. This is a steel substrate. We have used an aluminum oxide counterbody with a load or a contact pressure of 450 megapascal, room temperature, and 45% of relative humidity. And what you see is here this yellowish looking curve. That is the niobium system if you have copper intercalated atoms still present. Or in green, you can maybe slightly see it underneath. This is a system where you have iron intercalation in this niobium system. And depending on the intercalation, it can really have very much different frictional behavior. And we still try to figure out what is the reason for that. But the good thing is that you get really stable, very low coefficients of friction. And you will see on the further slides that they are even not affected by the atmosphere so strongly, which is a big benefit compared to TMDs and MXenes. The next interesting point is if you look at different counterbody materials. So we studied the role of adhesion. So apart from using aluminum oxide, we also use silicon carbide, Teflon, PTFE, and steel versus steel. And interestingly, if you use steel versus steel, the curve is really not looking very nicely. You have high friction, a lot of oscillations, and actually not really an improvement. Why? Because the TMCC powder doesn't stick to the steel counterbody. So there's a problem with sticking or adhesion, transfer of material to the counterbody, which is not the case for aluminum oxide or for silicon carbide, where you have really a very nice transfer of the powder also to the counterbody, and you can allow for a very good lubrication under these conditions. So there's more to get explored here in this context. The role of the counterbody, we started now some more measurements in the field of adhesion, just to see what is the physical explanation, the precise physical explanation for the findings, but this is something that is really, really interesting, how it depends on the counterbody material. And last but not least, I would like to show you some of the results we got under different atmospheres. So we also tested under air, but also under different, like nitrogen. And you see, it doesn't matter if it is air or nitrogen, the atmosphere has not such a strong influence on the TMCCs, which is good news because MXenes and also other solid lubricants like black phosphorus, they're very sensitive on oxidation. So if you keep them under oxidative environment, they may lose their lubricity very soon. There is only a little drawback. We also performed vacuum measurements under vacuum, as mentioned here in the graph. And you see that after 5,000 cycles, roughly, the stuff is going to fail. The reason is, however, that we have simply used, in this case, a really not compact film of TMCCs on the substrate, and there is a lot more we can improve. in terms of the surface deposition technique to get it more sticked to the substrate, and then we expect also that the measurement of under vacuum conditions will be much better. But if you compare on the right-hand side different materials like WS2, Maxions with the TMCCs, you can clearly see the benefit of the TMCCs under these testing conditions, of course, which is very nice. And you can also do, of course, a closer look at the chemistry and the microstructure. You see here, there's Auger spectroscopy results of the wear track, where you have actually a compaction of this powder. So this is only powder. This is no coating. It's really powder that we simply apply on the surface. And by simply applying a simple powder, it already gives us very nice results. You can then also go to the TEM again. You can also inspect the TEM cross sections, and you can measure the lattice spacings, and the lattice spacings are again according to the literature values that are reported. So very nice. You can learn a lot about these materials, and they have definitely some benefits, especially if you use them under different atmospheres. And there they have, I would say, a big advantage compared to other solid lubricants that are currently under research. We also did with Italian colleagues. This is the group of Maria Clelia Righi, and there is also Eduardo Marquez and others that I mentioned before. They also did DFT calculations of our system. And you can see here in this table number 1, there is a column for the work of separation, but also one column for potential energy surface corrugation, which is a kind of 2 indicators how easy shearable material is. And you see, if you compare the TMCCs with graphene or MOS2, they're very close together. Only the Maxine, the titanium-based Maxine, shows a much higher value for the work of separation and also for the potential energy surface corrugation. And if you then combine this with, let's say, a stress-dependent or pressure-dependent graph, you see here from 0 gigapascal up to 5 gigapascal, you can see in both cases, for the niobium system, but also for the tantalum system, that you will never reach across 0.05 joule per square meters. So that means that we have really a good shearability in the interface, and these materials are, from also the theoretical aspect, very interesting. And there is more work, of course, to be done also with regard to coatings and variations in the intercalation. But I would say this is a very promising field, and a big field where a lot of things can still be discovered. So last slide, because I think that is something that needs to get some attention in the community, especially based on some work we did on black phosphorus just recently. We recorded actually the coefficient of friction for isopropanol as a solvent, as most of these 2D materials are, of course, dispersed in a solvent. And a solvent can be ethanol, isopropanol. There are different ways you can use them in a dispersed media. And we use simply a steel surface, a droplet of isopropanol, and we heated this up to 100 degrees C or 250 degrees C. And you can still see that there is a very nice lubricity behavior of the isopropanol even at 100 degrees Celsius. Although the boiling point of isopropanol, by the way, is 80 degrees. Yeah? But you still see very low friction, very stable friction at 100. And if you want to get rid of the effect of the isopropanol, you really have to heat the entire stuff up to 250. And if you reach 250, you can be sure that the isopropanol does not play any more an effect, but maybe you also, of course, changed your solid lubricant, because such as black phosphorus, it starts degrading and getting more oxidized at 250 degrees and temperatures on. So that is something I want to really put your attention on, because I think there are a lot of papers published in the community where people claim this is because of 2D materials, but in fact what they measure is the effect of the solvent of isopropanol, for example, and you have to be really, really cautious that this is not an artifact from the solvent on top of your substrate. Otherwise, the entire interpretation is misleading. Yeah, wrapping up the stuff with the conclusions. I think I could show you that solid lubricants are, of course, the first choice if it comes to low temperatures or even vacuum, where liquid lubricants are presumably failing. But I could also show you that the world of 2D materials is really large. There's a lot of variation inside, and the exploration in the future will need some systematic approach to really put the stuff in material libraries and to really discover the things in a more systematic approach. Vaccines have a big potential. Problem is still the very energy consuming. They are also, in terms of sustainability, having some issues, and upscaling is maybe a problem to come to kilograms of amount easily. It's not that easy. On the other side, I could show you that some more recent materials like TMCCs have a great potential, and they are also independent of the atmosphere you apply. And but there is still a lot you can discover, a lot you can do. And finally, the role of solvents like isopropanol, I showed you on the last slide, is something really critical, and you must be really sure that you don't measure the artifacts from the solvent in your experiments. That's it from my side. I hope that you enjoyed it and that you learned something new in the world of 2D materials. And now I'm looking forward to your questions or comments. And thanks again for your attention.
Thank you very much, Karsten. Great presentation. So right now we're going to swap over to Philippe's presentation. So welcome him back on stage, please. Fantastic. Go. You just bring your slides up, Philippe. So we'll have this presentation from Artec Instruments now, after which we will have the Q&A session. So go ahead, Philippe, take it away.
Yes, thank you very much, Professor Gachot, for the very nice presentation. Artec Instrument is a scientific instrument manufacturer for surface characterization. And we have, in fact, a range of tribometers that are used, in fact, in this kind of research for the characterization of the coefficient of friction of materials. Artec Instrument has been involved in a lot of mechanical characterization, so not only tribology, and we are manufacturing advanced mechanical surface testing equipment for different solutions in the field of research and application for surface characterization. In fact, the company is based in San Jose, California, where the manufacturing of the instrument are taking place. But there are, in fact, office and laboratories in different parts of the world, including Switzerland, where I'm based, but also Japan, India, and China for different customer service and different sales channel and global partner worldwide. In fact, one of the big activity of Artec Instrument is, in fact, the measurements of coefficient and friction of wear of material, including MXN, as was shown by the previous presentation. But in fact, in the range of application of tribology, as you have seen, depends on a lot of different environmental conditions. There are also some vacuum material tester, high pressure tribometer, and specific application in tribology, including a fretting tester. So if you are interested in this kind of equipment involving as well different environmental conditions, you will be welcome to contact us for giving you more detail about the measurements capability. And in the range of tribology, most of the presentation have been involving a sliding condition, where you have a constant condition of sliding during tribological testing. But there are, in fact, other mode of testing, including twin roller or micro pitting testing for different bearing application or other kind of application. Tribology is covering, in fact, a large range of application, and we are, in fact, measuring the wear of material with general 3D profilometer. For those of you that were not so familiar with measurements of tribology, you have a very schematic but very explanatory mode of explanation of how tribology is conducted. It's basically based on applying a normal load and measuring the friction force while doing a rotative mode of displacement or a linear oscillation mode. So depending on the mode of testing, it's a relatively flexible test mode for tribology, where it's generally called the pin on disc tribometer, where you could do a rotation or a linear oscillation, depending on the application and the request of measurements for different kind of user. You have a small picture here how it's the rotary module for pin on disc tribometer. It is true that depending on the application, we can have application for very high speed, very high torque, or extremely low speed as well, depending on the mode of testing that is of interest. The fast linear reciprocating drive is allowing to have from very small displacement to high displacement with a relatively large range of amplitude, frequency, and speed of testing for this kind of mode of testing. It is true, as was shown before, that tribology depends on a lot of parameters: pressure, speed, and time of testing. But relative humidity must never be forgotten, as well as the surface condition of the material. There is a two-body test where you have upper sample and a lower sample, and the roughness, contamination, and lubrication of all of this material must be very well taken into account, and that has a big influence on the wear of material and the general result that you could have on a tribological test. Depending on the application, we can simulate what would be the contact condition. We are looking generally for an elastic contact on the material, and it is true that with a relatively low diameter of a ball, we can reach relatively high speed in a pin on disc tribology. It has been not shown today, but it's true that tribology needs some stabilization for certain range of testing, and it's very common to have a running in time period before stabilizing the coefficient of friction. Therefore, it's very important to determine what would be the time of testing in order to reach a certain stability for this kind of measurements. In terms of application, there are quite interesting evolution we can see. If we are testing coating, we can see a stable coefficient of friction. And then at the time of damage of the coating, see the visualization of what would be the variation of the coefficient of friction. And therefore, it's quite interesting to do 3D profilometry at the end of the test. So there you can take the sample at the end of the test and visualize with a confocal microscope as an example, what would be the wear on the lower part of the sample, and evaluate very precisely what is the wear volume on this kind of material. But at the same time, you could have a significant wear on the ball, and the 3D profilometer could be also very useful for this kind of characterization on the body. Then on a linear reciprocating mode, we can display what would be the positive and negative friction value while we are doing testing, and see variation of coating properties while doing linear oscillation on a pin on disc tribometer, and at the same time see over a period of time what would be the stabilization of the coefficient of friction. So as a summary, there are in fact in tribology and mechanical testing in general, quite a big number of requests with the current evolution in sustainability and measurement in different environmental conditions. Therefore, it's very interesting to have a large range of modules on different tribometer involving not only variation of speed and load, but also geometry of testing that could be available on different kind of tribometer. Professor Gasho is using a MFT 2000 tribometer, which is a tabletop instrument, but there are also MFT 5000 tribometers that represent very flexible instrument in terms of availability of many configuration of tribological tests, but also additional mechanical testing as scratch testing or instrumented indentation testing on this kind of instrument. And then the modularity is therefore combined nowadays with electrical contact resistance measurements or impedance measurements that have shown a big interest in the current evolution of the industry for very large range of application, combined as well with the temperature of testing. The integration of a 3D profilometer is quite interesting because you can really see on a very automated way what would be the wear of the material as you are doing tribological testing. I'll thank you for your attention. My presentation was extremely quick. I think some slides were gone very fast, but I hope that you had a few insights about what are the testing capability of Artec instrument, and if you are any interest in a specific instrumentation, we would be happy to help you to discuss your need. Thank you very much for your attention.
Thank you very much, Philippe. For anyone who hasn't downloaded the handouts, they're available in the handouts tab. So there is one for the Artec Instruments product overview and one specifically on the SMT 2000 nano indenter. So do give those a look. Very interesting. So what we're going to do right now is just release the link for the attendance certificate. There you go. And we're now going to do our questions. We just have these 3 questions for now. That's all we're going to do, as we're already a little over time. So we'll just keep it at these 3. Thank you very much, everyone. So our first one from Matt here, who actually has a couple of questions, who asks, are the tests upon molybdenum and tungsten plus SE done in a humid environment? And do you have any thought as to whether the results may differ in vacuum? And second, how is the powder applied? And would the application work in a zero-G environment, as in for space?
Yeah, good question. Thanks, Matt, for sending this question. So first of all, yeah, we've done this also under different humidities. Actually, as Philippe said, we are using MFT 2000 from Artec, where we also made adaptations. So we have actually constructed a kind of a environmental box around it, where we can even flood the chamber with nitrogen or argon. I mean, we are not going for vacuum at this point because simply, it would be too unstable, and we do not want to collapse the entire box. But for flooding it with argon or nitrogen, this perfectly works fine. And we also can change in some, let's say, in some variations, the relative humidity. So we did the tests, and also for the molybdenum and tungsten plus selenium, we see that if you do this under nitrogen, the things are even a little bit better. Which makes sense, because once you exclude the oxygen as best as you can, the results, I would say, are even more solid. But even if you, as I showed before, even if you do it under a normal atmosphere, you can clearly see the formation of selenites with molybdenum and tungsten. But under nitrogen, of course, it works even better. But this is no big surprise. I just recently attended a presentation from USPIKES, who is now very much working in the field of also testing under nitrogen atmospheres with his additives, and he has the same findings. And he also told me, he said, of course, if you exclude the oxygen, then the things are usually working much better than with the oxygen. But this is not true for the TMCCs that I showed you at the very end. So they don't take care if it is under oxygen or nitrogen or argon environment. It's always performing very nicely. The next point is powder applied. Very simple, very simple. You just take some grams of powder with a spatula, you just put it on a contact, you slightly compact it. So very stupid and very easy, but the reason is that we want to keep the things as simple as possible. Yeah. Also for the application later on, if you have to write a long report how to apply the material, it's for a company not of interest. But we also did stuff that is not yet published, where we deposited these materials as coatings. And with coatings, of course, I'm talking about the TMCC, especially for the coatings. Of course, it is much more professional, more reproducible, and more stable. But the routine we applied to powder is also very reproducible. So when we are doing 5 to 10 test variations, always comes up with the same result. So there's nothing wrong with this. Coming to the last part of your question, well, I don't know if it is for space. Well, it's hard to say. I mean, the idea is, of course, to have these materials for space environments. But of course, if it is a loose powder, I would go for the coatings, to be honest, and not for the loose powder. Yeah. But the interesting thing about the powder, if you are not under zero gravity, is that if you think of a little, let's say, box container, where with a timer, whenever you see friction is rising again, you adjust the timer, opening the box or the container and putting some powder inside the contact. It keeps the friction under control. That's the only way for the solid lubrication, by the way, to get it under control and to get it replenished. If you sputter, if you do PVD, CVD, once it's done, it's done. You cannot start in James Webb Telescope to have a PVD chamber up there. It doesn't work. So you need to have a simple solution, but of course, fair enough that zero G, that doesn't produce any problems in your case. That is a short answer, but of course, if you're interested in, I can send you more details about this as well.
That's great. Thanks, Karsten. Yeah, I'd be quite interested to see that further paper with those materials deposited as coatings.
Yep.
Okay, next question from Dirk, who asks, what is your prediction for the practical application of such exotic coatings, and when and how they may be commercially available, in your opinion?
Oh, that is a difficult question from Dirk. Well, the point is, first of all, yes, they are to some point exotic because they are not the standard. They are not the gold standard like MOS2. But if you consider MOS2 also has a long journey already. Yeah? It took a long journey. The problem in space is you have space heritage. We have some colleagues from NASA where we are currently writing a review paper about 2D materials. And one of our colleagues here, he explained to us what means space heritage. And even though you come alongside with a brilliant idea, NASA would say no, yeah, because it needs a long, long time. And long time means maybe 15, 20 years until you have proven thousands of times that it may work. And then if they are in a good mood, they say, okay, let's give it a try. The same is, by the way, true for aircraft engineering or aero engineering. I think there's Ronja maybe still in the list of participants today. She's from the German Aerospace Center in Cologne. And in DLR is the same. DLR is the same. You can have super cool coatings, you can have a super cool material, but it is about very safety relevant features. And if something happens, this is the point when the shit hits the fan, right? So you must be really careful what you apply. So coming back to the question of Dirk, I don't know when they will be available. Of course, I'm a researcher. My aim is to work on exotic stuff, but of course not for feeling bored, because I want to do something for the future. I also want to see if I'm lucky at one point that the things are getting into application. But this is, of course, not in the hand of university people. It really depends on if it makes the way up to space. It's a very long journey to make it up to space, because they are so conservative and they just do not want to have everything on board if it is not untested 1 million times. Yeah. Cannot say more than that.
No, it's a very, very good answer. Thanks. I mean, as well, I think will it operate in that environment? There's of course the atmosphere, which we discussed, and then also
of course
radiation tolerance as well, and multiple other things. I mean, I'm no expert on space applications, but there's there's a lot to consider there. Sorry, Dirk. So we'll just make one note of Dirk's sort of follow-up question there.
Just saw it. Yeah.
So these coatings will have to be validated in labs first to prove their reliability. Is there lab capacity available for this?
Yeah, as I said, we have these colleagues also from Woodward in the US, and also, as I said, one of our colleagues who was formerly at NASA, who is now Professor Nakran. So there are ways where we can have access to more elaborated testing facilities. Otherwise, I mean, we have also in our house. We have not for space, but we have for helicopter research. We really have a huge lab, mechanical engineering lab, where we test helicopter gearboxes, also with solid lubrication, by the way. And concerning the lab capacities, I wouldn't say that we have we don't have a huge aerospace lab, but we are well equipped. We have all what we need. We also can test under higher temperatures. I think there was another question with if we tested beyond 500.
Yes,
we tested up to 500 because we also got from Artec a temperature module, which allows us to go from room temperature up to 500 degrees C. Which is very nice because now we have everything. We have the MFT 2000, we have the box around for nitrogen and argon purge, and we have the temperature module from Artec, which all fits together. And we can do tests under higher temperatures, different humidities, different atmospheres. And this is very important for testing solid lubricants. The only thing missing is vacuum, but vacuum, we have colleagues in Wiener Neustadt. They have a vacuum tribometer where we have access to. And this is also what I showed you the results on one of the slides. So we can also test under vacuum conditions, not ultra high vacuum, but at least fair enough, 10 powered by -6 millibar, which is better than nothing. But you know how much a really good vacuum tribometer costs. This is another big investment for university people, unreachable like the sky. And here we rely on colleagues and friends and people helping us. If you know someone who has a very nice vacuum tribometer, I would be happy to be in contact with. And I just see that also Ronja posted here. I'm still here. Of course. I mean, maybe with DLR we can do something together.
There are a few in Europe now that are in Luleå University Technique and different institutes have now vacuum tribometer, which are also not like from industry closed laboratories that could be accessible for the future. But it's true that running in vacuum is not as easy as a tabletop tribometer.
Yeah, but you need to understand the vacuum performance, because if you argue with the space, of course, if your coatings or your materials do not prove in vacuum conditions, you don't have to argue with space, right? Because things in vacuum can be very different. And that's the reason why we always try to do also vacuum measurements to get a feeling how they behave. But if you know someone else, I mean, with Luleå, anyway, these are good friends and colleagues of mine. So I could ask Roland Larsson and his team up there in the north of Sweden, and let's see what we can find.
Yeah, hopefully, looking forward to seeing some of the results from that. Let's hope.
Let's see. I mean,
okay, so I think we're about 14 minutes over our stated time. So I think with that, I just have to say thank you very much for the questions, everyone in the audience. Those were great questions, great discussion. Thank you very much, Karsten and Philippe, for your
thank you, Sam, for the nice organization, and Professor Gachot for the nice presentation.
I just saw there are still some questions popping up, and maybe I can answer them also in a mail to the colleagues.
So I'll include you on when I put the information after the webinar together, so you can see those questions that we haven't been able to answer. Thank you very much for that, and also to everyone in the audience for asking those questions. But yes, so with that, unfortunately we're at time, and it's time to wrap up. So of course, once again, thank you for your talks. Thank you to Artec Instruments for the support for this event. We wouldn't be able to do this without our partners. So it's great to have to have people we can work with every month, and to be able to put on great talks such as this. If you want to look at more Surface Ventures webinars, you can look at our website. We have our archive of previous talks. Karsten has a talk that he's given with us before, as well as many others. You can register for our on-demand replays as well from our previous 2 talks. Our website will soon be updated with our upcoming mini symposium, the link for which is on screen now, so you'll be able to register for that. That is on the 17th of October, focused on the tribology of electric vehicles, with some great speakers as well. As another thing, visit the Surface Ventures LinkedIn, and you'll see all of our event updates there. You can read our newsletter, Modern Surface, and I'd finally like to ask if you know anyone that would be interested in these type of talks in our newsletter. Please do advertise this to your contacts, your colleagues. But with that, thank you very much for joining today, and have a great rest of your day.
Thank you.
Bye-bye. Take care.
Bye-bye. Bye-bye.
Thank you very much, everyone. Bye.